I did work offline, so off stream, I should say. Yeah, things work a lot better than before. At the end of the last stream. So this is my canonical cubic with extremes, local extremes. And we are only interested in the root of the flank that is the furthest away from the local extreme that is the closest to the x-axis. So, oops, the thing goes very fast now. So we put this thing above it, then of course that one is the closest to the x-axis. Therefore we are only interested in this root here. The green line goes through the found root, and the red line is the current starting point of the Haley method. So we start here, and then we do something, and then we find a better approach, and a better, and a better, and a better, and better approach until we have 20 digits or 17 digits, whatever. Then there is therefore in this case an offset between the initial guess and the actual root. And we see that in this graph at the same time as a log-log plot. So we see that at the moment for a very small C0, that is this is the log 10 of C0, so for C0 is close to 0, this would be 10 to the power minus 15. The error is super small, it's also 10 to the power minus 15. And anything less than 10 to the power minus 2 is good enough. So this whole part is good enough. It's unacceptable, more or less, that here we get something that's, yeah, larger than 100th. You can see that here. The red cross is where the slider is at the moment. So we make it smaller. And I set this thing at minus 100, so that is fifth, I guess. 100 is like here, I guess. And then you see that the starting point is almost on top of the root. So the Haley method iteration to find the actual root is going to be very, very fast. But if C0 is too large, then yeah, the error becomes larger and larger. And eventually, why do we just start at a completely wrong spot? It just flies off now. This thing doesn't move at all. It's just minus the square root of 3. Well, the root, of course, moves to minus infinity if we go up. And then it can take a while before we find it. Let's see if that works at all. Yeah, but it's still pretty fast. But so the guess is now initial guess is still minus the square root of 3. The actual root is minus 5, and we just take 1, 2, 3, 4, 5, 6 steps. So it's still incredibly fast. But why not have a better one? So if you read the description, you'll understand exactly what I'm going to do. I want to. That's one more thing I can show actually. So this was the guess here is now minus square root of 3. Let's replace that by minus the cube root of C0 plus 1 divided by the cube root of C0, which is very, very, very good. Well, equally good actually for infinite large values. Yeah, I don't know. It's very hard to stay within bounds. Stuff like this. I think that the reason is that the width is 0, and that is probably, or the height, as a result of getting not a number somewhere. After division by 0 or something like that. Or more likely taking the logarithm of a negative number. I think that I'm already taking the absolute value of this. So this would go wrong if this is 0 at most. But yeah, no, maybe it's too precise. Seems very unlikely. It is the y-axis range. That is not a number. Minus infinity, that could do it. I could I think this is the problem. Y min. Where exactly should I get the minus infinity? And that should happen if y is 0, right? No, the log. When the log 10 C0 is 0. Why the hell would I start at 0? Because I am. I have to skip 0. Let's just start at 1 here. Maybe that helps. Still not. Doesn't know what minus infinity is. also set that. We already had that. Damn it. Yeah, of course. I only had to set a condition. Anyway, I have a y. So what is the problem with the condition 3y is less than minus? Maybe it was interpreted as a floating point. No. Totally does not look less than minus. Oh, arg. Okay, now it's minus infinity. And why did that happen? Eight. So the problem is the div lambda. I suppose that for a C naught or C0 of 10 to the power 8, that is already so large that my guess is more or less considered to be exact. Okay, so what to do in that case? Because we definitely do want to something like let's say the maximum value here is, this is the y value of the difference, and I'm going to plot a log of that, so let's just limit it to about the minimum. Sorry, confused here. Okay, yeah, minus infinity is so small that I was confused because I have to clump it simply between minus 12 and whatever was returned by div lambda. That looks ugly. But again, ignoring the artifacts, you see now that for large C0, it dives down. And I had expected it to be as steep as the other one, which was more or less, I think, 1 on 1, or no, it has to be 3 times faster, right? There should be. I forgot how the other one looked like. The line. This line goes through that point, though, so that is 0, 0, just like the other one. And then at +5 we reached 9 or something. No, wait, 9 is here. A little bit less than 9. Okay, well, if you read the description that I wrote for this video, then you might understand why I'm confused. It was I had calculated that for. Let's see, what did I type? For large C0, a good approximation is minus the cube root C0 plus 1 divided by the cube root of C0. And if you fill that in, you get not the root, but 1 minus. Sorry, minus 1 divided by C0. Yeah, that's C0 to the power minus 1. So we would expect that we dive 10 at 10. That's like a line like this. It's steeper, which is only better, of course, but still, it's weird that it isn't just what I calculate. Anyway, you can also see here that for large C0, and then very rapidly we have our guess is almost exact, the correct root. You can already, you don't see the difference anymore. The guess is very accurately the correct root. And it doesn't matter how big I make it. Anything after, let's say, this point is good enough. So 0.7. But it's still log 10. So this would be already 10. You know, if C0 is larger than 10, then it's on spot on. I think that the thing was about around 4. I thought that for larger than 4, what is it? 10 log of 4. I don't even have. Oh, I have a log here. Yep, I have a 10 log. So the log of 4 is 0.6. So kind of between here, it's already pretty good. Nah, okay. But if you make it too small, then yeah, then you see that at some point it really starts to deviate. Ridiculously so. Goes to plus minus infinity now, I guess. Okay, so What I want to do is draw a graph with horizontally C0 and vertically S of C0. T description. Yeah, do I already have something that uses C0? It's the X range. This is U. And this is the log 10. I have the feeling that maybe I want to see them. Do I want to still to see that? Maybe. Maybe I should just make a third window. Yeah, why not? Window 3, and that is going to contain the S of C0. Not even sure if they require everything new, but call it the smoothing function. This is horizontal, and then vertically we set S as C0. So C0 itself, yeah, you kind of have to do it logarithmically. Just have to do it logarithmically. Yeah, actually. What do you mean still, Matt? I started to use Fluxbox when Plasma broke. I waited 2 years, just kept being broke, nobody fixed it. So I was completely fed up with it, and then I used Fluxbox, which is not broken. Let's just undo everything. I'm going to plot it in yeah, this one is but it's horizontally already the log 10 of C0. No, just keep it. Okay. It has to be the log 10, I think. Otherwise we can't show anything except a narrow range of C0. So that should have the same x range as plot 2 then. So plot 2 x range. This is of course plot 3. I don't know the y range yet, or do I? Well, that's going to the smooth function, so that's definitely going to be between 0 and 1. Let's see if this compiles and pops up a third window or not. Yep, smoothing function. The S of C0 and the log 10 of C0. Let's use the small one again. At least then I don't have those artifacts. Okay, how can we calculate S0? So I need something like we used for plot 2, but then not plot the log 10 of root minus guess. This is just a line. Yeah. So this is using the diff lambda to plot the difference. Now we want to plot something in the other window. And let's call that the S0 lambda. Sorry, S of C0. The input of that will also be the log 10 of C0. And we are definitely going to need a root. So I can just calculate C0 and then make the polynomial and get the root. No, I don't need a guess. Wait a minute. I need... okay, we do the following. So the root is going to be equal to the S of C0. Let me look at my description again, what I wrote. Just copy it. So we want to smoothly switch from this for small c0 to this for very large C0. Yeah, maybe the other way around. That means that for small C0 now this must become 1. It seems more logical to make it 0 for small C0. So let's change this to 1 minus that. Let's begin with an equal sign. So let's rewrite this a little bit. The 1 times that is minus the square root of 3. And then plus the square root of 3 times the s of C0. And this is minus C. You can keep that as one number. C plus 1 divided by C times the S of C0. From which follows that the S of C0 equals let's see, I did that correctly. 1 times that is that. Minus drops out. Square root of 3 times the S of that. We have minus that times that. Yes. So I can combine these two. Times S C0. Thus, this is the root plus the square root of 3 divided by that. Put the square root up front. This is the cube root of C0, and then we can calculate this. Subtract that from. I'm totally missing a parenthesis here, right? Subtract that from the square root, and we divide it. Use that to divide that. Hopefully I did not do that wrong. So for very large C0, the root is going to be equal to this, which means that we get the same value divided by itself, which is 1. To a very large C0 we get is this is 1, and then this is 0, so the root indeed becomes equal to that thing, obviously, but that means that I didn't make a mistake in these two lines. And for a very small C0, then the root is going to become equal to minus the square root of 3. So then this is 0 and this S becomes 0. So yeah, that looks completely correct. Return. And then like here, we use the log 10 of C0 on the x-axis. And then SC0 on the y-axis. Don't even crash. That is the smoothing function going from 0 to 1. Awesome. So now we must find a formula for this. It looks, of course, it looks very much like the sigmoid function, but then on a logarithmic scale. Let's print it from -3 something. It is not exactly a half at 0. That's interesting. Way from -3 to +3. It's the same as the plot 2x range. Yeah, what? -12? Oh yeah, okay. I had it very big. Let's do this. The cubic, the offset, and the smoothing function that we need. That looks very symmetrical, very symmetrical. I love it. Yeah, how to find out what function this is. Why is this thing so horribly symmetrical? Is it? Is it symmetrical? Looks like it though. Let's get rid of the squares. I'm really interested in where the next Bezier curve starts at the moment. And then let's draw the same thing twice, but then mirrored in a way. No, I first need to find the center point. So the exact value where it is a half. is this one? No, this one. So it is more or less 10. What? Impossible. I'll just use a tenth. No, this is 10. This is 1. Okay, more or less 1 then. But just okay, 1/10 to 10. That definitely will do. Type. .0. Maybe a bit much. Let's start. What the fuck? Oh, I'm an idiot. That must be the logarithm. You know, it would be so nice if this was a recognizable number. I need it more precise. No, actually I don't. But, you know, in order to recognize nice numbers, it would be nice if I just had it with the position of a double. I'll never know what this is, I think. And Google it. Yep. It's nothing. No, to the power of 3. Definitely does not ring a bell either. Just squared. Nope. Power 6. Not really. One minus that. Nah. Nah, there's nothing. I don't know. It has to be something, but well, would be pretty difficult to figure out what the exact formula is. Or would it? See, maybe I can do it. Oh yeah. Oh, of course you can do it. The only thing I need is the exact solution of a cubic. Some kind of formula. Yeah. Or we can play the iterative game with Wolfram Alpha on at high position. I don't know. I don't see it at the moment. Okay, let's just use this number. Or rather this number, I guess. So wherever we do this, and I now also want to plot plotted in the same graph. But M of mirrored. So it's mirrored here. I think something double locked in of C0. Yeah. Not the same, but shifted. Why would it be shifted? I mean, I mirror it and the point that we found here, to the very least, this point should equal that point. It's possible that it isn't. I don't know, something looks off. Currently this is exactly a half. Well, exactly. As exact as it can be drawn here. At the moment C0 equals 1. Why the hell would that be? Oh, I think I get it. Yeah. What I want is 2 times center minus that. I think. So at the moment that this equals center, you must pass center. I just want that if then it becomes larger, we go to the opposite side. So the minus sign is required, but I don't want to end up at 0, I want to end up center. So this must be 2 times center. Now this log value equals center, then we pass center. And if it gets smaller, then we get larger, what we pass, and so on. And yeah, this is just mirroring it in the horizontal line through a half. So this now should be mirroring it in the vertical line, and this mirrors it in the horizontal line, and then we can see if it is symmetrical. No, it's not. It is not symmetrical. Yep. Well, okay, so concentrating on half of the function anyway, and then maybe later on the other half, I'm going to plot C0 horizontally. And then, well, from 0, or yeah, I don't know, from small 100th to 1 to the center. No, that's comes 0 anyway. Now, yeah, I suppose we can approximate this with a cubic. Yeah, accuracy of this one is really not important. If it looks like it is more or less the same, it's already good enough. I could even just draw a straight line, I think. Like so. Or maybe, yeah, just a straight line. That seems good enough. Then it's off here, but yeah. Still need to find a function for this thing, yeah? Clearly it goes through 0, 0. So maybe yeah, just a quadratic multiplied with C0. And draw the same thing divided by C0. Hij zijt al ruwijsan. Thank you. This looks like a dented ellipse. Let me square it. Tja, what the fuck to do with this? It keeps looking like a cubic. This probably isn't. Oh. How did that happen? I just added one. Right. Nee, can't drag it. Did I forget then? What else do we need? Should be enough. I'm not doing anything different. Just add another slider to another plot. And I can drag this one and I cannot drag this one. What's the difference? Makes no sense. Oh, missing a handle input events. That's the reason. Yeah, that sucks. Because that hangs. That hangs until I hit space. Maybe you can just hit space on one window and then to the slider. Yeah, that worked one time. Okay, better solution. Simply replace this one. No, only handle inputs of 3. Yeah. Don't have a fit yet. Be nice if we could just pause a few points and then automatically get a quadratic polynomial that goes through those points. Seems I need a piecewise parabola solver. Just cut the function into pieces, and each of which we fit with a parabola until the thing is within some tolerance. And then I can just make a table. That would be the fastest, I think. So I have a Bezier fitter, and I could make a quadratics fitter, I guess. Probably a lot of copy paste. But it's 11 p.m., so I think I'll definitely not do that now. So let's have a quick look at how I could, let's say, generate a quadratic polynomial from 3 points. Yeah, 3 points. Or rather, so fit quadratic. Why the hell is this so slow? Yeah. Something wrong with the calculator thing. This top was using very much CPU. And that happens when you put it on the calculator, when you get a calculator thing. Broken shit. Okay, what was I going to type? Yeah. Fit quadratic through 3 points. And of course they have to use little numbers. Nobody's interested in numbers. Why? Numbers, numbers, numbers. Channel problem. I'm going to vote this up without reading it, just because it doesn't work as numbers. Thank God. So yes, we have x1, y1 is 1 point, and that is on the curve. And so same for point 2 and 3. And you can solve it like that. Ta-da! No, that's copied it. It's not copied it. Let's type it over. I sure hope I can include point here. Do I even have point? I probably don't have point. Blink, blink. Point. This is in math. I definitely have no point. Cairo no point. Should this not be in math? This one can't be, but it is in namespace plot. But I mean, of course, this one then. Just simply a wrapper on two doubles. Definitely should be a math, really. Together with direction and vector and stuff. Which is again a lot of work. So yeah, let's not do that today. I'm going to play a game of chess and then call it a day. Hey, look at my rating. I'm back at 1950 something. It had dropped below 1800. I was so worried. But apparently I have not turned senile yet. What is a side quest? I play chess every day before I go to bed. I just stop coding and then I go to bed. At the end I'll play chess. Gives away a pawn. I don't see it. I get a pawn. I'm definitely behind in development, but some free development here. Doesn't even threaten mate because it can escape. But okay, we'll defend it. I think I do this and then nothing. Well, then he can go here, attacking my knight and the pawn, but then I can't go back because then I lose my bishop. And why did he not go immediately here? That would have been way better. Shit. I'll have to do this, I think. And he could sacrifice. Oh, sacrifice. Thing is pinned. He just takes it. Can't do that either. Can't push the pawn. Maybe we should let him take. I go back, take, I go here, and then check again, of course. I can go here. Man, this is really bad. Oh wait, I see something. I can do this. And then do that. Now my knight is protected and he can't give mate. And I even threaten to retreat the knight again now with a check on the queen. This is probably a good move. He was kind of threatening to take it. Yeah. I'll take it. To defend the rook, of course. Plus I threaten to do this and have again a tempo on the queen. But I could would have been better to wait with that until I played the bishop. It seems, but okay. Where to go to? Running out of time. Let's go here to defend that. Otherwise, you could just take it because this one is pinned. Now I'm +3. Oh, he's gonna take my rook. Fuck me. He takes my rook. Yeah, that's not so good. Then I'm -2. Shit. Not good. Not good at all. Oh no, there my queen is overloaded. Knight comes here. Queen defends 2 pieces. Yeah. Impossible. Yep, +9. So I did not give up for nothing. Gonna play one more. Not good. I don't win, of course. Still 1950. I can't play this one because the knight hangs. Then Let's fucking check. Why? I thought I saw something a second ago. I wanted to play my knight to here. Yeah, and then I can go there. That's what I wanted. And I didn't do it. So suppose yeah, I'm just completely winning. This is also still winning, I think. Oh no, no, this is mate. Oh yeah, of course you can. Well, you can ignore it. Check. This was my plan, but then he does that. Ah, and the rook works. Oh, of course. Oh fuck! I thought that moving the rook didn't help for some reason. I think yeah, I do this and then I'm still mate. I thought he just had mate now. But this is bullshit because I have a hole there. I'm so stupid. That time pressure. I had the feeling I had to move very fast or something. Damn. Okay, let's quit before I lose even more. Good night.